The universe is vast and full of wonder. It stretches beyond our imagination, filled with countless mysteries and phenomena that continue to baffle and inspire us. Among the many celestial wonders, stars hold a special place in our hearts and minds. Among its many marvels are stars, giant balls of burning gas that light up the cosmos. These luminous spheres are the beacons of the night sky, guiding sailors, inspiring poets, and fueling the dreams of astronomers. But what exactly are these brilliant objects made of, and how do they come into existence? But have you ever wondered where stars come from? The journey of a star begins in the most unlikely of places. Vast, cold clouds of gas and dust that seem almost lifeless at first glance. These regions, known as nebulae, are the stellar nurseries of the universe. How do they form, and what are they made of? The process of star formation is a complex and fascinating one, involving the interplay of various forces and elements over millions of years. It all starts with the raw materials scattered across the cosmos. The story begins with huge, cold clouds of gas and dust scattered throughout space. These clouds, often spanning light years in diameter, are the remnants of previous generations of stars that have lived and died, leaving behind the building blocks for new stars to emerge. These clouds are mostly made of hydrogen and helium, the simplest elements in the universe. Hydrogen, the most abundant element, serves as the primary fuel for the star's eventual nuclear fusion, while helium plays a crucial role in the later stages of a star's life cycle. Over time, gravity starts to pull these particles together. This gravitational attraction causes the cloud to become denser and more compact, setting the stage for the birth of a new star. The process is slow and gradual, taking millions of years to reach fruition. Slowly but surely, the cloud collapses in on itself. As the particles draw closer together, the cloud's density increases and the temperature begins to rise. This marks the beginning of a transformative journey from a cold, dark nebula to a bright, shining star. As the cloud shrinks, it spins faster and faster, like a figure skater pulling in their arms. This increase in rotational speed is due to the conservation of angular momentum, a fundamental principle of physics that governs the behavior of rotating objects. The center of the cloud heats up immensely due to the increasing pressure. As the core temperature rises, it reaches a point where the conditions are ripe for a remarkable transformation. The intense heat and pressure cause the hydrogen atoms to collide and fuse together. When the temperature and pressure at the core reach a critical point, something incredible happens. Nuclear fusion begins. This process releases an enormous amount of energy, causing the core to ignite and shine brightly. The fusion of hydrogen into helium is the fundamental reaction that powers the star. And so, a star is born. This new star will continue to burn for millions or even billions of years, providing light and warmth to any surrounding planets and contributing to the ongoing cycle of stellar evolution. From the cold, dark depths of space, a brilliant beacon of light emerges, illuminating the cosmos and reminding us of the incredible processes that shape our universe. Deep within the core of a newborn star, a cosmic dance is taking place. This dance is not one of elegance and grace, but of immense power and energy, a dance that has been ongoing since the dawn of the universe. It's called nuclear fusion, the process that powers the stars and creates the building blocks of our universe. This process is the very heart of stellar life, the engine that drives the brilliance of the night sky. But what exactly is fusion? How does this incredible process work, and why is it so vital to the cosmos? Imagine tiny atoms, the fundamental building blocks of matter. These atoms are the smallest units of chemical elements, and they are the foundation upon which everything in the universe is built. In the intense heat and pressure of a star's core, hydrogen atoms are forced to collide with incredible force. The conditions are so extreme that these atoms, which normally repel each other, are pushed together. These collisions are so powerful that they fuse together, creating a new element, helium. This transformation is not just a simple change. It is a profound alteration that releases a tremendous amount of energy. This fusion process releases an enormous amount of energy in the form of light and heat. The energy produced is what makes stars shine so brightly, illuminating the vast expanse of space. This energy is what makes stars shine so brightly and provides the heat that counteracts the inward pull of gravity. Without this energy, stars would collapse under their own weight. For millions or even billions of years, stars continue this process of fusing hydrogen into helium, maintaining a delicate balance between gravity and energy. This balance is crucial for the stability and longevity of stars. As stars age, they go through various stages of evolution. The fusion process changes over time, leading to the creation of heavier elements, and eventually to the star's transformation into a different type of celestial body. In some cases, the star's life ends in a spectacular explosion known as a supernova. This event scatters the elements created in the star's core across the universe, seeding new stars and planets. This cosmic recycling is a fundamental part of the universe's life cycle. The remnants of old stars become the building blocks for new stars, continuing the cycle of creation and destruction. Our own sun is a part of this grand cycle. It formed from the remnants of previous stars and now provides the energy necessary for life on Earth. The fusion process at its core is what makes life possible. Scientists are studying fusion not only to understand the universe, but also to harness its power for future energy needs. Fusion has the potential to provide a nearly limitless source of clean energy. Experimental fusion reactors are being developed around the world, aiming to replicate the processes that occur in stars. If successful, these reactors could revolutionize our energy systems. As we look up at the stars, we are reminded of the incredible processes that power them. Fusion is not just a scientific concept, it is a testament to the beauty and complexity of the universe. The fiery dance of fusion continues, a never-ending performance that shapes the cosmos and inspires our quest for knowledge. It is a dance that connects us to the very fabric of the universe. Like humans, stars have a life cycle, evolving and changing over time. This journey is a fascinating process that spans millions to billions of years, depending on the star's mass and composition. From their fiery birth in stellar nurseries to their eventual demise, stars undergo a series of transformations that shape the universe around us. Their story is a tale of birth, growth, transformation, and eventual death. Stars are born in vast clouds of gas and dust known as nebulae. These stellar nurseries are the cradles of star formation, where gravity pulls together the material to form protostars. Over time, these protostars gather more mass and heat up, eventually igniting nuclear fusion in their cores. The path a star takes depends largely on its mass, with heavier stars living shorter, more dramatic lives. Massive stars burn through their fuel quickly, leading to spectacular and often violent ends. In contrast, smaller stars like our Sun have longer, more stable lifespans, gradually evolving over billions of years. Once a star has consumed a significant portion of its hydrogen fuel, it begins to change. For a star like our Sun, this marks the transition from the main sequence phase to the red giant phase. The core contracts and heats up, while the outer layers expand and cool. The core contracts and heats up even further, allowing it to fuse helium into heavier elements like carbon, nitrogen, and oxygen. This process of nuclear fusion releases tremendous amounts of energy, causing the star to shine brightly and expand even more. As the star evolves, it expands significantly, becoming a red giant or supergiant. These phases are marked by dramatic changes in the star's size and luminosity. The outer layers of the star are pushed outward, creating a vast, glowing envelope of gas. These stellar giants are much cooler than their younger counterparts, emitting a reddish light. The cooler temperatures are due to the expanded outer layers, which spread the star's energy over a larger area, reducing the surface temperature. During this phase, stars can be hundreds of times larger than our own Sun, engulfing nearby planets in their fiery embrace. The sheer size and luminosity of red giants and supergiants make them some of the most awe-inspiring objects in the night sky. Their eventual fate depends on their mass, with some ending their lives in spectacular supernovae, while others shed their outer layers to form beautiful planetary nebulae, leaving behind dense cores known as white dwarfs. Section 4. Forging elements inside the cosmic crucible. The heart of a star is a cosmic crucible, forging elements that are essential for life itself. As stars age and their cores become hotter and denser, they continue to fuse heavier and heavier elements. After helium is exhausted, the core collapses again, and the temperature and pressure skyrocket. This allows the star to fuse carbon and oxygen into even heavier elements like neon, magnesium, silicon, and sulfur. This process of element creation continues, building up the periodic table element by element. Each stage of fusion releases energy, sustaining the star against the relentless crush of gravity. But this process can only go so far. Section 5. Iron's Limit. The end of fusion's reign. Deep within the core of a massive star, the fusion process grinds to a halt when it reaches iron. Iron is the most stable element in the universe, meaning it requires more energy to fuse than it releases. This creates a critical problem for the star. Without the outward pressure generated by fusion, gravity takes over, causing the core to collapse in on itself in a matter of seconds. This collapse triggers a cataclysmic explosion, a supernova. The energy released during a supernova is unimaginable. For a brief period, a single star can outshine an entire galaxy. But more importantly, these explosions play a crucial role in seeding the universe with the elements necessary for life.